Good evening. Tonight, how satellite eyes in the sky are changing the way explorers hunt for gold, and why one tech company's work in Kenya could reshape mining discovery, cut costs, and reduce environmental harm. Tonight's story begins with a familiar problem. Gold is rare, and finding it the old-fashioned way is expensive. Traditional exploration means boots on the ground, surveys, rock and soil sampling, long drilling campaigns, often across hundreds of square kilometers. That work can take years and cost millions, and even then there's no guarantee you'll find enough metal to justify the bills or the environmental disturbance. What if you could dramatically shrink that search area before you ever put a drill bit in the ground? That's the promise of satellite-powered exploration. The technology making that promise real is not science fiction. It's the same family of Earth-observing satellites that scientists and farmers rely on every day. Those sensors capture light beyond what our eyes see. Infrared bands, shortwave infrared bands, and those extra colors let analysts detect minerals, vegetation cover, and moisture differences across the landscape. Using spectral band combinations and ratios, it's possible to highlight minerals associated with hydrothermal alteration, the kinds of chemical changes in rocks that often accompany gold mineralization. Researchers and remote sensing specialists combine seasonal composites, topographic masks, and index calculations to produce prospectivity maps that rank areas by how likely they are to host gold-bearing systems. One company taking this approach and publishing a public case study is Farmonaut. Working on a 26 square kilometer area in Kenya, Farmonaut used satellite time series imagery, seasonal median composites, band ratio mineral indices, and topographic masks to produce what they call a gold potential index, a single heat map that integrates multiple mineral signatures, seasonal stability, and terrain constraints. The result, a ranked polygon-based list of high-priority targets ready for targeted field checking. Farmonaut's write-up of the case study lays out the methods and the practical outcome: fewer square kilometers to check in person and a clearer path to where drilling should be focused. That's important for three reasons. First is cost. When you restrict your field program to the highest-ranked anomalies, you save on mobilization, drilling, and manpower. Second is speed. You accelerate decision-making by focusing on a short list of prioritized targets. Third is environmental impact. Less exploratory disturbance across wide tracts of land means reduced damage to habitats and local communities. We should be clear, satellites don't replace fieldwork. Remote sensing delivers probabilistic targets, essentially where to concentrate your ground truthing. In the Farmonaut case, the satellite workflow emphasized temporal stability, meaning signals that persist across wet and dry seasons, to avoid chasing transient effects like crop cover or recent fires. That's a standard best practice in modern Earth observation-based exploration and reduces the chance that a promising pixel is just an ecological or agricultural artifact. This approach also draws on academic work done in Kenya and neighboring regions. Case studies have demonstrated the utility of remote sensing for mapping hydrothermal alteration zones, even in vegetated or semi-vegetated terrains. Precisely the kind of settings where careful seasonal analysis and topographic filtering matter. Those studies provide methodological backing for why the satellite-first approach can work in East Africa's complex landscapes. Here's how the workflow played out in practical terms. Farmonaut collected 182 cloud-filtered, quality-controlled scenes and created seasonal medians to suppress noise. They computed multiple band ratio indices tuned to alteration minerals, combined those indices into a weighted gold potential index, and then applied masks, removing water bodies, dense forest, and steep slopes to isolate realistic drillable areas. These areas were converted to polygons and ranked by size, contrast, and temporal persistence. In short, the satellite data was turned into a field-friendly to-do list. Now, some may wonder about resolution limits. Satellite sensors operate at tens of meters per pixel, enough to map alteration trends and geological structures, but not to spot the very smallest veinlets. If a project needs finer detail, higher resolution commercial imagery, airborne hyperspectral surveys, or targeted ground geochemistry are the next steps. Think of satellites as the where-to-look tool, not the final arbiter. Studies show satellites have strength for raw mineral mapping and that combining datasets often improves detection in different geologies. Finally, this isn't just an academic exercise. Farmonaut today offers a platform and apps that slice satellite data into actionable products for agriculture and increasingly for mining prospectivity, packaging the same remote sensing science into subscriptions affordable for smaller operators as well as bigger companies. The company's online resources and mobile apps illustrate how an end user can go from satellite data to a ranked target list without building a full geoscience team in-house. So what does this mean for Kenya and other emerging exploration frontiers? It means faster, cheaper prospecting with less environmental disruption when used responsibly. It means local regulators and communities can get earlier, clearer information about where exploration will happen, potentially improving consent and planning. And it means small operators can leverage the same data-driven edge that used to be reserved for major corporations. Satellite-powered exploration isn't a silver bullet. Ground truthing and sound geology still rule the day, but it's a powerful new first step. From studio to savanna, the tools that map crops and water can now guide where we search for the underground riches that have driven economies for centuries.